up, guys? Welcome back to another Algebra 2 review session here with Mr. Gaines as we prepare for our final exam. This is the fourth video of this series in which today we will take a look at some graphing, some work with imaginary numbers, and some simplifying of radical and rational expressions. So let's jump right into some example problems. In problem 37, it says, graph the function shown below, including the asymptote, the initial point, and at least two other points to show the growth or decay rate of the graph. So we have f of x equals the negative log base 2 of x minus 1 plus 3. And this function can be put into our graphing calculator, which we will get to here shortly. But before we do, I want to talk about some transformations and how they affect the graph. So all logarithms have a vertical asymptote. This vertical asymptote can be found by taking the horizontal shifts. This graph has a horizontal shift to the right 1 unit. So we're going to shift this graph again to the right 1 unit, and that's going to give us our vertical asymptote. This vertical asymptote will be at x equals 1. So that takes care of one of the pieces of information, the asymptote. We need an initial point. All exponential functions have an initial point that starts at 1, 0 prior to any transformations. So we're going to begin here at 1, 0, and then we are going to shift to the right 1, which puts us at 2, 0, and then do a vertical reflection with that negative out in front, or reflection across the x-axis, which would keep us in this location, and then shift up 3. And so this would be the location of our initial point. This point is going to be at 2, 3. So you can label that point or sketch it just on the grid. Now, we can get other points for the graph based on the base of this function. The base tells us the distance to move from the asymptote. So every time I move up or down a line, I'm going to move a power of 2 from the asymptote. And exactly which power of 2 depends on which direction we move in. Remember, this has been reflected. So as I move down, let me sketch this in here. As I move down, it's going to go further away from the asymptote, and as I move up, it's going to go closer towards the asymptote. So if I move one line down from our initial point, this is going to be 2 to the first power units from the asymptote. So this point would be at 3, 2. If I move another line down, this would be 2 to the second power units from our asymptote, or 4 units from the asymptote, which is going to be at 5, 1. If I move down another line, it is 2 to the third power units from the asymptote, or 8 units from the asymptote, which would put us at 9, 0. Now, if I move up a line from my initial point, so here's my initial point at 2, 3. If I move up one line from 2, 3, I would be 2 to the negative first power units from the asymptote, or 1/2 unit from the asymptote. So this would be at 1.5, 4. So here I've included far more than just 2 additional points to the initial point to show my exponential growth, but this allows me to sketch in the curve. Now, this is how I would graph without the use of technology. If I wanted to use my graphing calculator, I would still find the horizontal asymptote in the initial point as we did to start the problem. Then if I wanted to make sure that I have all the remaining points accurate, I can input this equation into my calculator. Now, some calculators have the option of using a change of base. Some do not, but we can use the change of base formula. So we can input this as log base 10 of x minus 1 over log base 10 of 2 plus 3. And if I am to look at the graph, it gives us a picture of this graph. It does not continue vertically on the graphing calculator as the calculator starts to discontinue the graph where the asymptote when it approaches the asymptote. But if we look at the table, we can see we have the points 2, 3, 3, 2. We don't have the point 4, 1.45, but we do have the point 5, 1. And if I go down further, I have the point 9, 0. So we have correct points on this graph. Problem 39, it appears that we skipped problem 38, which is okay, but problem 39 on the packet says a friend claims that x equals 2 minus 3i is a solution to the equation x squared minus 2x minus 1 equals 0. Do you agree or disagree? And show your work to support your answer. Well, I could go through the process of solving this equation, but a little bit easier than that, I can check to see if an answer is a solution by substitution. So I can substitute in 2 minus 3i into this equation, and then evaluate the expression to see if this will equal 0. So remember, when you square a binomial, you square the first term, 4. So 2 squared is 4. I take the two terms, multiply them together, and double that. So 2 times negative 3i would be negative 6i, times 2 would be negative 12i. And then I double the last term. So negative 3i squared would be 9i squared. I'm going to distribute my negative 2 for my second set of parentheses. So that would give me negative 4 plus 6i minus 1 equal to 0. I can evaluate this expression. The 4 and the negative 4 here would eliminate each other. This negative 6i can be, or negative 12i can be combined with the positive 6i, give me a negative 6i. I can take 9i squared, and remember that 9 or I squared is negative 1, and simplify that into a negative 9. So this would be negative 6i minus 10. And we can see that this does not equal 0. And so we would disagree. This is not a solution to our equation. Now you can also check that on the graphing calculator. So if I go over here to the graphing calculator, I can use my graphing calculator to evaluate the expression just to, I did the multiplication by hand to show that work, but I can also include a check on the calculator here by typing in the equation and inputting 2 minus 3i for x, as we have written down. And then the calculator will simplify it for me. And it confirms that it is negative 10 minus 6i, which is the same as negative 6i minus 10. So this is no solution. Taking a look at problem 40, it says for each of the following, write the expression in the standard form for complex numbers, a plus bi form, and show your work. So we need to simplify each of the expressions and put them in that given form. So in 40a, what I may notice is that I can simplify inside of this set of parentheses. Remember, when I have a negative inside a square root, I can turn this into a positive by removing I. So I is equal to the square root of negative 1. And so what I've basically done here is, I'll go ahead and write this step. You wouldn't need to show this step, but what I've basically done here is break this into 9 times 3. I'm going to break it into 9 times 3. I'll come back to that, times a negative 1. I broke this into these pieces because now I can simplify 9. The square root of 9 is 3. The square root of negative 1 would be I. So what I would have is 3 root 3 times I. Now I do need to simplify this expression by distributing the negative 2. So this would give me a negative 2i. Negative 2 times 3 root 3 would be negative 6 root 3. I times I would give me I squared. And we can remember that I squared is equal to negative 1. So negative 6 times negative 1 would be positive 6. So I would have positive 6 root 3. Now I want to make sure this is an a plus bi form, so I'm going to list my real number first, followed by the subtraction here because it is negative, of my imaginary number. Let's go ahead and take a look at b. In b, the directions remain the same. The concepts remain the same. So I'm going to simplify this. I'm going to first take a look at the root and see that this root can be simplified into 81 times negative 1. I left it as 81 because you can take the square root of 81. This would be 9. And the square root of negative 1 would be I. Now I can combine my i's, so I'd have negative 3 plus 8i. So as we combine the i's, we can add and subtract their coefficients. Now, part C has multiples of I. And so if you remember back to the very beginning when we talked about imaginary numbers, we said that I was equal to the square root of -1. Then I squared would be -1. I cubed then would be the same as a negative I, and then I to the fourth power would be the same as I squared squared, which is 1. So negative I would also equal negative root -1. So basically what we can do is we can look at this as multiples of 4. So why multiples of 4? Well, any multiple of 4 is just going to be 1. So I could break I to the 45th power into I to the 44th power times I. And I can break 3i to the 21st into 3i to the 20th power times I plus 1. The reason I'm breaking them into these numbers is because those are multiples of 4, which means their value is just 1. So I would have -2 times 1, which is -2, times I, plus 3 times 1 times I, plus 1. So now I can combine my i's and list my my real number first, and I would get 1 plus I. This can be checked on the calculator. So if I check this on the calculator, I can do -2 I to the 45th power plus 3 I to the 21st power plus 1. And see that we do in fact have 1 plus I here. So values of I as the power increases will repeat this pattern shown here to the right. Now part D. In part D, I want to do what's called rationalizing the denominator. Currently, I have an imaginary number in the denominator. I want to rationalize that. And we can rationalize that when it's a binomial by multiplying by the conjugate. So the conjugate of -3 plus I would be -3 minus I. And I'm going to multiply by -3 minus I over -3 minus I, the same thing in the numerator as the denominator, to not change the fraction. In the numerator, I can simplify by distribution. So this would be -6 minus 2i. In the denominator, I can simplify as when we multiply conjugates, it's the square of the first term. So -3 squared would be 9, minus the square of the second term. -I squared would be I squared. Now, I can simplify because I know that I squared is equal to -1. So this would give me -6 minus 2i over 9 minus a -1. And 9 minus -1 is the same as 10. So -6 minus 2i over 10. I can split these up, right over here, I can split these up into two fractions. So -6 over 10 minus 2i over 10. This puts me in the form a plus bi. Simplifying those fractions, I would get -3 over 5 minus I over 5, or we could write this, if we wanted exactly in the a plus bi form, 1/5 I. So I'd simplify each one of my fractions there. So in order to get an I out of the denominator, if it's a binomial, we want to multiply by its conjugate. That way we will turn the I into an I squared and therefore be able to create real numbers. Enough with the imaginary numbers. Let's go ahead and just deal with some real numbers, and specifically variables that are greater than 0, so positive real numbers. In 41, it says simplify each of the following expressions using roots or rational exponents as needed. Rationalize all denominators, meaning we want to make sure all denominators are not part of roots, and assume that all variables are greater than 0. Show your work. So we need to simplify the equation here seen in 41a. Now, if I look inside the roots, I may notice that I can't really simplify in either one of the roots. So what I can do here is combine roots. Remember, one of our properties that we had with roots is if roots are being multiplied, you can multiply their radicands. So I'm going to multiply the inside expressions. So this would be by taking 4a c cubed times 4a in the numerator, I would get 16a squared c cubed. Then in the denominator, I'd get b times 5c cubed, which would be 5b c cubed. Now I can simplify this expression. You can see that the c cubes will cancel or divide out to give me 1. So this would be 16a squared over 5b. Remember, with roots, I can take, this would be the same as square rooting the numerator and square rooting the denominator. If I square root the numerator, that becomes 4a. So the root of 16 is 4. The root of a squared is a. And this is over root 5b. Now I do need to rationalize the denominator, so to get rid of the square root, I need to multiply by a value that would change the radicand to something that could be square rooted. In this case, 20 or 5b. If I combine the numerator, it just stays 4a over 5b. But if I combine the denominator, it becomes root 5b times 5b. I can multiply the radicands to get 25b squared. And 25b squared can be simplified. Square root of 25 is 5. The square root of b squared is b. So our final simplified expression of this, rationalizing the denominator, would be 4a times root 5b over 5b. In part B for 41, I'm only working with real numbers and no variables here. So we see that I have two binomials, and so I can multiply these together by distribution. So 1 times 3 would be 3. 1 times root 5, remember you would multiply together the coefficients, and if there are roots, I'd multiply together the radicands. So this would just be positive root 5. I would take negative 2 root 5 times 3. This would give me negative 6. I would multiply negative 2 times 3, root 5. Then for the last distribution, I would get 2 root 5 times root 5, which would be 2 root 25. So now I can simplify these. I would still have that 3. If I have equivalent to 1 root 5 and I take away 6 roots of 5, I would be left with a negative 5 root 5. Now I can also simplify the square root of 25 here. So the square root of 25 is 5, which would make this equation at the end 2 times 5, which is 10. Now I can combine my constants, 3 and 10, to get 13 minus 5 roots of 5. Now we can't do this exactly in the calculator, but we can check the answer in the calculator. So if I type in this equation into the calculator, 1 minus 2 roots of 5 times 3 plus root 5. It's going to give me a rounded answer, and that rounded answer is approximately negative 18.18. Now I can go ahead and take my answer here. Oop, looks like I made a mistake. So we can take my answer here that I have for 13 minus 5 roots of 5 and type that in, and notice here that these are not the same rounded answer, and I found my mistake. My mistake came right here when I multiplied, hopefully you caught this, when I multiplied a negative 2 root 5 to positive root 5, that should be a negative 2 roots of 25, which would end up giving me negative root 10. So my answer should be 7 minus 5 roots of 5. So if I check this again with, a negative 7 minus 5 roots of 5. Now I can see my decimal approximations, the one up here from the equation they gave us, or the expression they gave us, and the one down here from the simplified version do match, and so I do have the correct answer for this one. In problem 42, now we're dealing with variables again, and this time rational expressions, or fractions. So we need to simplify each of the rational expressions. Now in problem 42a, I have a division. Remember, division of a fraction is the same as multiplication of its reciprocal. So x plus 4 over x minus 2 divided by the second fraction is the same as multiplied by 2x squared minus x minus 6 over x plus 4. Now remember, I can simplify this by eliminating factors that are equivalent in the numerator and the denominator. So essentially, I can connect the fractions. So I'm going to have x plus 4 in the numerator. And I'm going to go ahead and factor 2x squared minus x minus 6. So if I factor this, this will factor into two binomials. And then I would have a 2x plus 3 and x minus 2. So 3 times negative 2 would give me the negative 6. Obviously, 2x times x would be 2x squared. And if I check the inside distribution, that would be negative 3x. That would be 4x. Sorry, I switched my signs. 2x plus 3 and x minus 2. So this would give me negative 4x and positive 3x, which does give me the negative x in the middle. So here I have a factored version of 2x squared minus x minus 6. Now, I can simplify this by comparing factors in the numerator to factors in the denominator. Factors in the numerator that are equivalent with those in the denominator would divide out, and so the end result would be 2x plus 3. And this would be where, if we wanted to, we could look at domain restrictions where x cannot equal 2 and x cannot equal negative 4, but that's something we'll come to later when we start looking at solving equations. So if you just listed this as 2x plus 3, that would certainly be okay. Let's take a look at b. Now there's a number of different ways to complete this. This is a complex fraction. One of the ways to complete it is to make sure that all of the fractions within our fraction have the same denominator. So what I'm going to do here is I'm actually going to look in the numerator. So the fraction in the numerator, r over 9, r squared minus 6r plus 9, and factor that expression. So the denominator would factor into r minus 3 squared. In my denominator, I have 1, which cannot be factored, and 3 over r minus 3. So if I want to make sure all of the denominator, all of the fractions, all of the terms within my fraction have the same denominator, I can do some multiplication to make this happen. So in the bottom right, I would multiply by r minus 3 over r minus 3. In the bottom left, I would multiply by r minus 3 squared over r minus 3 squared. What this would give me, and I'll simplify as I go along, but what this would give me is r over r minus 3 quantity squared over, I'll go ahead and write this as r squared minus 6r plus 9, that is the quantity r minus 3 after you square it, over r minus 3 squared, plus 3 times r minus 3, or 3r minus 9. Let's distribute that, so plus 3r minus 9 over the quantity r minus 3 squared. Now, we did the proof for this, the algebraic proof for this in the notes. So if you want to look back on that, you can find that proof. But once we have all of the fractions within the compound fraction to have the same denominator, those denominators will eliminate one another. And so I can simplify what's left. So what I would have in the numerator is r. In the denominator, I would have r squared minus, so I'd have a negative 6r plus 3r, so minus 3r. And then positive 9 minus 9, those would cancel out. I can simplify this further by factoring the denominator. So this would be r times r minus 3. Now my r's, common factor in the numerator and denominator, would eliminate, and that would leave me with 1 over r minus 3. This would be the final answer for that evaluation. So here we have an evaluation or some simplifying of rational expressions. And this is a good place to stop with finals review video number 4. As always, thank you guys for tuning in, and I'll see you soon.